In 2022, a team of physicists announced they had created a wormhole, not inside a particle accelerator, not in deep space, not in some underground facility with miles of superconducting magnets. On a chip, a quantum computer chip sitting in a lab in California. The announcement detonated across global headlines. Major science publications treated it as one of the most significant physics results in a generation. And in some ways, they were right to be excited. But buried beneath the coverage was a question almost no one in those headlines stopped to ask. Was it actually a wormhole? Here's the situation quantum physics is now confronting, one that goes far beyond any single experiment. Quantum computers are approaching a threshold, a point where they can simulate systems so complex, so deeply entangled, that no classical computer on Earth can independently verify their output. That sounds like progress, and in one sense it is. But it creates a scientific problem that nobody has fully solved yet. If the machine produces a result you cannot check, how do you know it's real? How do you tell the difference between a genuine discovery about the universe and a convincing artifact produced by the simulation itself? That is the question now haunting the frontier of quantum science. And to understand it properly, we're going to cover three things in this video: the wormhole experiment, the scientific battle it ignited, and a second quantum simulation from 2025, one that modeled the potential collapse of the universe as we know it. Let's go back to 2022. A collaboration of physicists used Google's quantum processor, called Sycamore, to run a physics experiment. The processor has 53 qubits in total. The experiment actively used 9 of them. What they were attempting to simulate was something called the Sachdevyi-Kitaev model, the SYK model. It's a theoretical quantum system that behaves chaotically at low energy scales, and it has a profound mathematical connection to black holes through a concept called the holographic principle. The holographic principle is one of the strangest and most consequential ideas in modern physics. It proposes that the full behavior of a three-dimensional gravitational system, like a black hole, can be completely described by a two-dimensional system without gravity. The physics on the boundary encodes everything happening in the volume. This is not science fiction. It is a mathematically rigorous conjecture that has occupied theoretical physicists for decades, and it sits at the intersection of quantum mechanics, general relativity, and string theory. If the holographic principle is correct, then simulating the right kind of quantum system on a processor might mathematically behave like a tiny holographic universe, one that contains the equivalent of a black hole, connected to another black hole through a wormhole. Now here's what the researchers actually observed. A qubit of information was encoded on one side of the 9-qubit system. After a carefully engineered sequence of interactions between those qubits, interactions designed to mirror the SYK model, that information reappeared on the other side. The team interpreted this as the information traveling through a wormhole inside their simulated holographic universe. Not teleported through standard quantum channels, but threaded through a gravitational shortcut in a miniature model of spacetime. The paper was published in Nature. The coverage that followed was immediate, global, and enormous. Within weeks of publication, a team at UC Berkeley published a pointed and formal challenge. Their argument came in 2 distinct parts, and both of them struck at the core of the original team's interpretation. First, the SYK model used in the experiment had been dramatically simplified to fit on 9 qubits, and in the process of compressing it down, something critical had been lost: chaotic behavior. In real gravitational systems, around actual black holes, the dynamics are deeply, genuinely chaotic. That is not an incidental feature. Chaos in the holographic framework is part of the mechanism that makes the connection between the quantum system and the gravitational analog mathematically valid. Remove the chaos, the Berkeley team argued, and what remains is no longer a gravitational analog. It is a quantum circuit. The second part of their challenge was more technically damaging. They demonstrated mathematically that several of the specific signatures the original team cited as evidence of a wormhole, the precise patterns in how information moved across the system, could appear naturally from the simplified model itself, without any wormhole, without any holographic physics. The model's own construction was sufficient to produce those signals. The original team responded. The debate moved through formal academic channels. By 2025, Nature published a structured critique alongside a full response. Both papers are peer-reviewed. Both teams hold their positions. As of 2026, the measured consensus among physicists is this: the quantum teleportation was real. The experiment was genuinely interesting science. But whether it demonstrated holographic wormhole physics, That question is still scientifically open. Now here is where the story shifts to something larger and in some ways more unsettling. In 2025, a separate research team ran a different quantum simulation, not on Google's Sycamore. On a D-Wave quantum annealer equipped with 564 qubits, one of the largest quantum processors ever deployed for a physics experiment. What they simulated was something called false vacuum decay. In quantum field theory, the vacuum is not simply empty space. It is the lowest energy state a quantum field can occupy. But theory allows for a troubling alternative. The vacuum we inhabit may not actually be the lowest energy state available. It could be a false vacuum, a metastable condition, like a ball resting in a shallow dip on the side of a hill rather than at its lowest point. If that is true, then somewhere in the universe, a bubble of lower energy true vacuum could form spontaneously. Once formed, that bubble would expand outward at the speed of light, converting everything it encountered into a region governed by different physical constants. Nothing inside its reach would survive. Nothing would outrun it. This is a real theoretical prediction, and the D-Wave team observed it in simulation. They modeled how these vacuum bubbles form and propagate, watched the transitions occur in a controlled quantum environment, and found results consistent with the underlying theoretical expectations. This experiment has not generated the same controversy as the Wormhole paper. The physics is well understood, the methodology was clear, and the results have held up to scrutiny. One important caveat: the model was one-dimensional. The real universe is three-dimensional. Whether the bubble dynamics survive in a full representation remains a question for future experiments. Both of these experiments, separated by 3 years, using completely different hardware, studying entirely different phenomena, point toward the same fundamental challenge. And it is the challenge that now defines where this field is heading. As quantum processors scale, they enter a regime where classical computers can no longer keep pace. This is often described as quantum advantage, the threshold beyond which quantum machines can do things that classical machines simply cannot. It is genuinely a milestone worth celebrating. But it creates a scientific crisis that nobody has fully answered. In the Wormhole experiment, the model was small enough that classical computers could partially replicate it. That is precisely how the Berkeley team built their critique, by running a classical simulation of the same circuit and showing that the model's behavior could be reproduced without any holographic physics. But as processors grow to hundreds of qubits, then thousands, eventually millions, that classical crosscheck disappears permanently. There will come a point at which a quantum computer produces a result that no classical machine on Earth can verify. At that point, how does science proceed? Physicists are actively working on this. Approaches include cross-validation between different quantum architectures, error mitigation and correction at scale, and formal mathematical proofs that bound what a specific circuit can and cannot produce. But none of these are solved at the scales that matter. The Wormhole controversy made this problem visible in a high-profile way. It showed that even a small, well-documented 9-qubit experiment could generate a dispute lasting years, not because of hardware failure, but because of a deeper question. Did the model reflect real physics, or did it reflect itself? So where does this leave us? Quantum simulation is entering a new era. The experiments covered in this video would have been technically impossible a decade ago. Today, physicists are running quantum simulations of holographic universes, black hole interiors, gravitational tunnels through space-time, and the theoretical mechanism by which the universe itself could catastrophically transform, all on machines that sit in climate-controlled laboratories. That is remarkable. It is a genuine scientific achievement, and it should be recognized as one. But the headlines that followed experiments like the Wormhole paper were not precise reflections of what the science showed. The experiment demonstrated quantum teleportation inside a carefully designed exotic model. Whether it demonstrated holographic wormhole physics is a question the scientific community has not resolved. The difference matters, not because the experiment failed, but because the precision of the claim determines what the result actually teaches us about reality. The more important story is not about any single experiment. It is about a new kind of scientific frontier, one where the tools are growing more powerful than our current ability to validate them. We are at the beginning of an era in which quantum computers may allow physicists to experimentally probe quantum gravity, black hole thermodynamics, the holographic structure of spacetime, and processes that govern the deepest layers of physical reality. That potential is real. It is significant. And it is unlike anything physics has had access to before. but realizing it will require more than bigger processors and more qubits. It will require building the scientific infrastructure to know, with confidence, whether what the machine is showing us is a window into the universe or a reflection of the machine itself. That problem is not solved. It may be the defining challenge of quantum science over the next decade. And the experiments being run right now, however contested, however preliminary, are the first steps toward answering it. The era of experimentally probing the universe with quantum computers has begun. The question is no longer whether we can build the machines. The question is whether we can learn to trust what they tell us. If this kind of science is what you're here for, subscribe. There is more coming on quantum computing, black hole physics, and the experiments pushing the boundary of what we understand about reality. Drop a comment below. Do you think the wormhole experiment captured real physics, or was it a simulation artifact? I want to know where you land on that. See you next time.